It was to revisit these two presentations with you, which are very technical, very complicated. So in fact, the work currently being done is to shift from mineral to biological. The agriculture that is being prepared is an agriculture, I'm going to provoke everyone a bit by saying it will be organic, but bio with a capital B, a small dash from the computer of the 6, or I don't know which letter it is, and a big L with logic. This biological agriculture that is coming is not built on NPK, it is built on carbon and on the cycles of biology. And so it is something that is complex, because ultimately the question to ask is why plants in nature grow without any fertilization. And mine, I am forced to fertilize almost like crazy to achieve it. And so by zooming in on this, we asked ourselves questions. A soil that has no organic matter, it looks like what we see it in our fields here in the Gers, but increasingly throughout France, there is not much that grows. And then finally, if you remove a farmer, you have a succession of plants that will establish themselves to create an ecosystem. And at the beginning, ultimately, these plants have great difficulty in truly growing. It's a lawn, it's a few small shrubs, it's pioneer plants, and it will take at least 100 years. So the more degraded it is, the more time you need to create a forest. And this forest, what does it tell us? It tells us that it's the maximum yield of the plant that wins the battle. That is to say, the biomass produced is enormous. Curiously, with the plants, we have restored the soil's fertility, meaning we have stored a lot of organic matter, which is called humus, but there is also a lot of organic matter that degrades quickly. So what is this mess? Why is it that in soil where plants grow, there is a lot of organic matter? And probably the answer that comes is that this organic matter is a very particular substrate that promotes plant growth. That is to say, photosynthesis alone is not enough to increase yield. So a large part of the yield would come from the soil itself, that is to say, carbon, stored in the soil by the biological and plant system. And so it gave us some rather striking formulas. When the soil consumes carbon, it produces nitrogen. The more carbon it consumes, the more it produces. And so there is indeed a problem of heterotrophy in plants. That is to say, it is likely that photosynthesis alone is not capable of sustaining the productivity of plant systems. A part comes from this famous stock that it establishes and from which it draws to increase yield. So we make paths, we conduct experiments. And I did some with Francois, and it was with Francois that we opened this debate, first among ourselves. And here, this is the first time we are truly bringing it to the public, because this debate needs to be created. The young or the not so young, like Nadine, we have them investigate in the bibliography. We see that we know a lot of things, that it is very complex. When you go into detail, it is very complex. And I'm used to saying that we will first simplify the reasoning to establish a guiding thread on which we can add complexity later. So here we use the POR method, we complicated things first, and now we are going to simplify. The title of the presentation is Plants Grow on Their Own. They have a secret and they eat meat. To put it simply, that's how it will work. In fact, we got a little glimpse with our famous amino acids that are directly involved. So at some point, proteins will be needed, which will arrive somewhere. And we will realize that our bacteria, etc. Maybe the roots perform lysis on microbes, meaning they will consume them in a certain way to absorb them. Because these microbes in their life and recycling cycle will be enriched with amino acids, and the plant prefers amino acids over nitrate. And we learned that plants were nitrate pumps. No. In nature, nature tries to minimize nitrates as much as possible, or even eliminate them entirely. So we have an agronomy that is completely built on laboratory errors. Because if I add nitrates on their own, yes, indeed, the plant absorbs nitrates abundantly. So we say, great, nitrate pumps. But when we combine the three together, amino acids, ammonium, and nitrates, the nitrates are not absorbed at all. Ammonium is absorbed more, and amino acids first. So there's something going on. Who would have thought of creating a fertilization plant for my vineyard, my wheat or cornfield or whatever, by fertilizing the soil with amino acids? Well, I'm very interested in that. Why? Because it ends my spreading plans. It's nitrogen that doesn't exist in the administration. Great. Oh, I do what I want. Let's go and take a closer look. So, I am currently experimenting with the first amino acid-based fertilizers. And when I started this investigation a few years ago, that's why we need people to bring back science, because my speech is a bit provocative. But overall, these amino acids will nourish the plant. And here, I have an experiment where the farmer will tell me that it's not bad at all. Next year, we remove all the nitrogen and only do this because it's the best batch of the system. So let's allow ourselves to be surprised. So we have plants that grow, we don't always know why, but we have understood that they grow on their own because the nitrogen comes from the air. This is fundamental. There is no limiting factor. Nitrogen in nature and in my agricultural fields all the time. We conduct experiments. So these are experiments on market gardening. Come on, the classic thing, I have a meadow. So it's here. No, what is it? There you go. I have a meadow. Wait, let me go back. I have a meadow, I plow it, I plant things, they will grow, I harvest. Well, the harvest from this system where ultimately we will mineralize the organic matter, have risks of erosion, organic, not organic, same debate. That's why we have to break down the barriers, organic farming or not. We're in the same boat with the same problems. And at some point, what's going to happen in there will produce more or less between 20 and 40 tons per hectare of squash. Why not? It can bring in money with vegetables. It costs me a bit. We can do so. That's dollars. Because we presented this at the symposium on living soils in Montreal. So over there, we talk in dollars. So you'll excuse us, but $1 equals €1. And then we'll get there, more or less. And we're in it. Another experiment is the one we did with living soils. So what do? We take our meadow, we're going to cover it all with a woven top. So this will prevent photosynthesis or the plants die. Through the woven tarp, we will plant squashes and we will harvest them. So here, some red curry squash. No worries, this is clean, so you don't even need to wash them. It's perfect. When you do specialized gardening, you realize that without doing anything, just with the degradation of the meadow under the top, you will produce between 30 and 50 tons of a red curry squash, meaning we produce as much as if we fertilize and demolish the meadow. In fact, even more, since we've practiced, we produce more today. So there's a problem, meaning it grows without fertilization and without soil work. And there's absolutely no need for all that for it to work. And that these are the experiments we can easily afford in a system of small plots through market gardening. So it gave us a living soil market gardening project. It's booming. There isn't a single market gardener who wants to start without doing this. However, it will be necessary to learn how to do it. It's a little more complicated. And finally, we realized that the only way we might fail to grow there is perhaps by digesting organic matter. Things are happening. So we continue. Here we have the French champion. His name is Christian Abedi, of these new systems in large-scale farming. In large-scale farming, what do? We create a winter cover crop, which will be returned to the soil. At the time of corn sowing, we slightly change the densities and the ways of sowing corn. That is to say, it's at 40 centimeters wide and no longer at 80 centimeters, to put it simply. Because in fact, it covers better, grows faster, and there is more vegetation. In short, we are in the world of plants. So we plant everywhere, and in the end, we achieve very good yields. And we started to configure the systems So there is still a little bit of phytosanitary treatment. Well, we weed. There you go. We learn. Well, what interested us is the potential of the plant biomass that will be returned to the soil. It's the famous soil ration. It's a theme we developed. We said that the soil must consume carbon. So, just as we have a ration for cows, we have a balanced ration for humans. There probably exists a balanced ration for the soil, except that we don't quite know its nature. We have some ideas. Dead leaves are well digested by the soil, branches too, which gave us ramial chipped wood. So we have interesting investigative tools. There are roots that die, so the soil is indeed consuming something. The question is what, how, at what speed, how much it needs, etc. And when we took stock of these cornfields, we still produce 10 tons of dry matter from straw, 13 tons of dry matter from root deposition. That's the corn crop, meaning the roots re-inject a lot of carbon into the soil. So precisely, we are beginning to discover that it's not that simple. The exudates, there are sugars, glucose, undoubtedly there are amino acids somewhere, and that could benefit the growth of the corn. There is all the plant cover here, which will also be returned, so it nourishes the soil. So here we have more legumes for corn. And finally, the soil's ration is 35 tons of dry matter per hectare per year. In this model, things we've never seen because we've never really looked at them this way. And that is the food for biological activity. And so when you take your 35 tons of dry matter, that gives you 14 tons of pure carbon that will be returned to the soil's ration per hectare. So suddenly I think to myself, hey, I'm sending carbon into the soil. And wouldn't this carbon help increase the system's productivity in addition to photosynthesis? Hence, the possible staggering increase in yields, the limit of which we do not know. Corn is listed in the books as 35 tons of grain. For the world champions, because there are world production competitions for corn, and for wheat, they say, when done in a greenhouse, it's 35 tons of wheat per hectare of grain, so the straw and the roots and everything with it. So there is an enormous amount of carbon in these systems, and we are barely capable of producing 5 times less, that is to say around 6 or 7 tons, when everything goes well. So we are very poor at it. Overall, when we are farmers, but not just farmers, it's the entire sphere of agricultural production that is poor at it, because it has never focused on making a plant function according to its natural biological construction, which is 4 billion years old. And so that puzzled us a little. And then we realized that this cover will also produce 200 or 300 units of nitrogen. And that corn, to achieve its grain yield, needs 300 units of nitrogen. There is nitrogen that enters through the plants, and you don't need to add more. It's something that surprised us a bit, and in the end, we continued the discussions. What is fertile soil? Plants produce the soil's carbon, the leaves, the roots, the wood, etc. But it's the soil that produces the plant's carbon. We can clearly see that in the desert, where there is no carbon in the soil, it's very complicated to start growing a plant. We say it's the sun, it's the lack of water. And then, in the end, we never really asked ourselves if it was truly the lack of carbon. And the guys who experiment with BRF in the middle of the desert, immediately, boom, the yields explode. We protect a little from the sun. It's enough to put a veil that lets light through, but protects, that provides shade. And when you put carbon in the soil, it takes off. So there is a problem. Does the yield come from the soil, or does it come from the air? There. I guarantee you that you're not proud because you've always been told that photosynthesis is in charge. Yes, it is in charge, sure, but it's not enough. Plants have invented this system, a carbon reservoir in the soil to increase productivity. The model, we know it. The whole world worked on this in the 90s, and we adopted that source. It was the Americans who did this for us. Living soil is a recycling unit. and we will have to tackle this. I produce, I use, I recycle, because I recycle everything. I never lack anything. Period. Sustainable development, that's what society must do. It's the cycle of plants on living soil. The entire society of this plan adopting this model is urgent, urgent, urgent. Growth is over, degrowth is over. All of that, you throw it in the trash, it makes no sense. Nature has been practicing sustainable development since the dawn of time, with zero CO2. In the air, look closely, exactly 0.04%. There's no CO2 in the air. I create all life on Earth. And so for it to work, there is indeed a trick. We share, I don't hoard wealth. A billionaire is failing in sustainable development. Why? Because he keeps the money without reinvesting it into a production cycle mainly. So we will realize that it's free. All life on Earth is created freely thanks to an electron engine, which is a photon, which is photosynthesis, inexhaustible energy and rare carbon that we will recycle all the time. All the excess carbon, the plants have put it somewhere. Guess where? Oil, coal. We buried it in the ground because probably it is useless for growing a plant. Okay? Because it works with almost nothing. And it's because there is almost nothing that we are here. So that's a little bit problematic. And then finally, we look at photosynthesis itself. In the atmosphere, you have 750 gigatons, which are billions of tons of pure carbon. There you go. 0.0%, that's it. And the photosynthesis of all the plants on Earth captures 62 gigatons from the air every year. So that means in 10 or 12 years, you would have no more CO2 in the air for photosynthesis. However, life on Earth has been around for a long time. So, fortunately, there are polluters who send CO2 and other things. Carbon dioxide, methane into the air. Long live the cows. Yes, because they will eat the plant that has absorbed the carbon, and we will pollute cheerfully, because we need to send back as much greenhouse gas as possible so that photosynthesis can continue. I protest against the fools who say that cows are responsible for the greenhouse effect and climate change. That's stupid. More stupid than that, you die. I am responsible as a human being. It's me who is not doing my job well. And so, at some point, we will need to dot the I's and cross the T's, call a spade, a problem a problem. CO2 is not a problem for agriculture. It's a problem for my industrial society, and I don't know who else. But when we look at all our models, they are linear. I mine iron, I transform it, etc. I make cars out of it and then throw them away. Well, cycle that model for me. Produce, use, recycle. And if we knew how to recycle our cars, our computers, I don't know what else, there would be no resource problem. It's obvious. We have it right in front of us. We don't know how it works. There is engineering to be deployed. I guarantee you there's work to be done. And so we are in this, and we work with this model. And finally, we get a glimpse of the complexity with amino acids, etc. How does it work? That's fertile earth. I have my goose foot, it grows, and then what does it tell me? It does photosynthesis, it absorbs nitrates, no nitrates in a soil. For the, for the plants to grow. So I have a nitrate pump, it's called a goose foot. And finally, it tells me that I produce wood, the stem is a stick of wood. So first info, no nitrate in the soil, I grow, I make wood, I nourish the soil with wood. It's impressive, you say, wow, it grows with wood. And I say, no, it grows with ammonium nitrate. No, it doesn't grow with ammonium nitrate. The proof is we are in an agricultural crisis. And then finally, we will intervene here. The straw falls to the ground. It is yellow. You've all seen it. I harvest, it's yellow. Okay. When you leave the straw on the ground, it turns black. So there are little critters that hydrolyze the carbon in the straw and capture nitrogen from the air. They're called azotobacter prefixes. and you start with the plant to produce animal proteins, bacteria. I am bacteria, a bacterial construction. I am meat. You say, Don, the leaf falls to the ground, the wood falls to the ground, and it's the meat that eats it. Yes, because that's what nature invented. As soon as there is a plant, it's the meat that will break it down. The plant eaters are living beings rich in proteins. It's meat. Now, bacteria equals meat. And there you have simplified your debate, so we can make it more complex. There is science for that. And finally, here, a kind of soil soup is going to be made. On the soil, it has turned black. So, the soup is on N24th. It will be absorbed by earthworms. There you go. We make soup. The earthworms eat that. So, they are going to eat protein. Microbial, they are going to eat meat. There you go, let's put it simply. And they will digest that with a little bit of cellulose. There is still some fiber left, and we will mix that with the soil, and there we will create the clay humus complex. In fact, it's a super excrement. The earthworm eats and it pees and poops. And there, it's the phenomenal crisis. In the word pee, you should hear urine. Urea, the nitrogen of nature, that's why plants grow so well on their own, is urea. And urea, in its degradation phase, will give rise to your ammonium that we saw earlier. The famous NH4+. Never nitrate. Always ammonium. And so this is, the first phase is here. You're going to make a kind of glue. We know well that poop sticks. So its structure, your habitats, and the poop. It will be eaten by poop eaters who, in turn, pee poop. Okay. And so these eaters, mainly bacteria, will produce chemical molecules. And actually, this is more up to date, considering what we know now. Now, we know that there real amino acids appear, which come from this pile of meat. And finally, the plants, what are they going to do? They are going to use this pile of meat here. They will perform microbial lysis to absorb not only the mineral elements that all the biochemistry has released, but also the protein amino acids contained in the bacteria and certain fungi. It works. And so, now, I'm going to have a big societal and civilizational problem. Since I just discovered that as soon as the plant produces carbon-based organic matter and it touches the soil, it will be digested by a digestive tract, ultimately, which is filled with meat. And we could even simplify by saying that it's because plants eat meat that they grow so well. And so now I have a problem in my field. Should I use ammonium nitrate or amino acids? That is to say, a plant-based bacterial slurry full of meat to the brim so that it grows as best as possible. And ultimately, we will realize that this transfers carbon, since there is carbon everywhere in amino acids, and it transfers nitrogen, since we will find nitrogen everywhere, in addition to urine and ammonium. And so, ultimately, you have a magic formula. The more I feed the living system of the soil, the recycling unit, the more mineral elements and amino acids I will have. To produce, the more I feed, the more I produce, and the yield explodes. And photosynthesis is the engine that adds just a little bit of carbon. But since there isn't enough, I have to put it back immediately. And so these systems, they work very well. You can fertilize. All the fertilizers come here into the bacteria section. So we know that, let's not dwell on it. Look at what the scientists are doing for us. Degradation of a leaf up to a certain point. Giving us what will ultimately serve as a pantry for the plants. That is, living beings that will be eaten in turn. So the debate is very simple. We used to do things like this. We only put straw, we grow the plants, so it has yields as high as a mineralized system where we add NPK. That's why at the inner in Grignon, they simply forgot a system where we feed the soil with carbon. And it should be brought to light. It's not too late, because precisely it is likely that this system that consumes carbon will surpass all the others in a few years. We could take the soil where we have never put anything, and surely, if we feed it with carbon, in a few years, it will be superior to the others. So it would be very interesting to do it. And so we realized that we have implemented fine nitrogen systems. So it works like this. Nitrogen comes from the air. It will be captured by bacteria in the straw. It will mineralize, and the plants absorb nitrogen. And now we need to add, given the knowledge we saw this morning, the amino acids that appear in the nutritional chain. And so we will be able to exclusively fertilize our plants with amino acids. So that becomes super interesting. Well, we had put in a lot of things. Okay, here's how it works. Basically, we have only one enemy in this natural agricultural system, and that's the sun. And that we hadn't understood. That is to say, as soon as the sun touches the ground, you have a drying, oxidizing, and destructive power. Powerful. Whereas the sun should touch the engine, which the photosynthesis of the leaf. And as soon as you have the sun touching the bare ground, you are unable to recover the biology of living beings, because all these living beings that will consume the first carbon on the soil surface, which make the soup, are sensitive to ultraviolet rays. In fact, me, alone, naked in the sun, I die. Well, a bacterium too. And ultimately, who can withstand the sun all alone, naked? It is mainly pathogenic bacteria, thermophiles, which can withstand very, very high temperatures, but those we are much, much less interested in. So we are a little unhappy with that. So we tell ourselves that the soil must remain in a black box with a lot of food and moisture. So there you have it, it's over. We know that this straw will go from 100 to 24, and then overall, every time the soil digests a ton of straw and feeds this meat circuit to grow the plant, it will also capture almost 10 units of nitrogen from the air. There you go. We found all this in the bibliography. I thank Nadine very much, who delved into reading all of this. We can clearly see that it's complicated to convey all this in a complex and scientific way. I prefer to simplify the debate. Look closely at the ecosystem. The more straw I consume, the more nitrogen I produce. 10% comes with the rain or snow. The nitrogen from the air. 60% of the needs for everything that plants require to grow comes from this organobiological cycle. So, from the mineralization, the degradation of leaves, and the microbial lysis that will provide amino acids and urine. And finally, 30% come from the stock and recycling of humus itself. Hence, the importance of this stock, because in fact we can predict that if you have biology and humus, you are self-sufficient in your fertility cycle. So this is lacking everywhere, and biology too. It still doesn't exist in agronomy books. It's NPK, always and again. And finally, what we know with Marcel Boucher is that 1 ton of earthworms produces about 600 units of nitrogen in the form of urea urine. There, you are astounded. So I understand that I, as a farmer, have never applied enough for it to really grow at the level it should. But all the administered fertilizer plants prohibit me from doing that. 600 units of nitrogen, you don't even think about it. Anthosiane Max. And so the organobiological systems, they are going to completely shake up all our methods, all our standards, right? All our notebooks, spreading plans, etc., etc. All of that is going to be shattered under the potential and the growth of biology. There you go. Thank you. Marcel Corral.